Hello everyone. So in this session we are going to study modulus of elasticity. So there are three types of elasticity corresponding to three types of strain. The first one is Young's modulus corresponding to linear strain. The second one is bulk modulus corresponding to volume strain. And the third one is modulus of rigidity or shear modulus that corresponds to shear strain. So we will start with the longitudinal stress or strain that corresponds to Young's modulus. So a body under the application of a deforming force along the direction or certain direction that produces a change in length per unit original length is called longitudinal strain. The deforming forces applied per unit area of cross section is called longitudinal stress. The ratio of longitudinal stress to longitudinal strain within the elastic limit is called the Young's modulus of the body. This Young's modulus is represented by the letter Y or E. Now, this Young's modulus is also sometimes known as coefficient of elasticity. So if force F is applied normally to the cross-sectional area A, the longitudinal stress is F upon A. And if small l be the change in length produced in the original length capital L, the longitudinal strain will be represented by small l by capital L. So that Young's modulus capital Y can be expressed mathematically as F upon A whole divided by small l by capital L, giving us the mathematical expression of Young's modulus as F into capital L upon area into small l. Remember, capital L represents the original length and small l represents the change in length. This relation holds good for both extensive stresses and compressive stresses. The unit of Young's modulus is Newton per meter square, which is same as that of stress, as strain is unitless. So if we want to define Young's modulus, it can be stated that if a material of a unit length and unit cross-sectional area could be pulled so as to increase the length, which makes it double the original length, then the force applied would measure the Young's modulus, the value of Young's modulus. So it is experimentally observed that the elastic limit is exceeded when the extension produced is beyond 10 raised to minus 3 centimeter per centimeter. So the material will break down before the defined extension is produced. Okay, now for the better understanding of Young's modulus, let us consider an example of rubber and steel. Normally, we believe that rubber is more elastic than steel because it requires much smaller force to stretch it, and therefore its elasticity is much smaller than that of steel. Why? Because it requires a much smaller force to stretch it. So in fact the value of Young's modulus for rubber is 150 times of that of steel. If a material is elastic, it means that it should have large range of elasticity. A crystalline body can be stretched to less than 1% of its original length before reaching the elastic limit, while rubber can be stretched up to 80% of its original length. So in this way, steel is more elastic than rubber. So to define Young's modulus, so a material is said to be more elastic when it have a large range of elasticity. Okay, so now let us study bulk modulus. So if the deforming force applied normally to the surface of the body is uniform, the volume of the body will change, keeping the shape unchanged. The deforming force per unit area is volume stress, or sometimes known as normal stress, and the change in volume per unit original volume is known as volume strain. So the ratio of normal stress or volume stress to the volume strain is known as bulk modulus, or sometimes it is also known as coefficient of cubical elasticity. It is denoted by the letter K. So if F be the deforming force applied to the body uniformly and normally, so F be the deforming force applied uniformly and normally to the body, then the normal stress will be F upon A. And if small v be the change in volume produced per unit original volume capital V, then the volume strain will be the ratio of small v upon capital V. So the bulk modulus is defined as normal stress or volume stress upon volumetric strain. Mathematically, it can be expressed as F upon A whole divided by small v upon capital V. Remember that small v represents the change in volume while capital V represents the original volume. So the mathematical expression of bulk modulus will be FB upon A into small v. Also, F upon A is known as bulk pressure. So it can be also expressed as P into V upon small v, where small v is the change in volume. So the unit of bulk modulus is also Newton per meter square, which is same as volume stress, as there is no unit of strain. Also, the inverse of bulk modulus is known as compressibility, which is denoted by C, which is nothing but inverse of bulk modulus 1 by K. So sometimes bulk modulus is also known as incompressibility. Okay, so now let us go to the modulus of rigidity. So a deforming force is applied on a body such that it produces a change in shape, keeping the volume unchanged. The deformation produced is due to the movement of layers of the body over one another. It is measured by modulus of rigidity, which is represented by eta. So as shown in this diagram, consider a solid rectangular cube fixed at the lower surface DCGH. A tangential force is applied along the direction shown in the figure. Due to this force, a couple is produced by an equal and opposite force coming into play on the lower fixed face DCGH. As a result of this couple, the layers of the body between two parallel faces ABFE and DCGH slide over each other, producing a shift on the top surface ABFE relative to the bottom face DCGH. So what happens? The lines AD, EH, BC and FG joining these two faces slide through or turn through an angle theta, which is measured in radians. So here the ABFE face is said to be sheared through an angle theta, which gives the shear strain or the angle of the shear. So this theta is nothing but the shear strain, which is the ratio of AA dash to dA, or we can also say small l to capital L, where small l represents the change produced due to this deforming force and capital L is the original length of the face or the line. So shear strain or simply shear can be defined as the relative displacement between two planes separated by a unit distance is known as the shear. And the tangential stress is nothing but the tangential force divided unit area of the face ABFE. So here the modulus of rigidity of the material of the body is the ratio of tangential stress to the shear or shear strain. So it is mathematically expressed as Ft into capital L upon area into small l, where small l is the change produced due to the deforming force applied to the body. So this is all about modulus of rigidity, which is also having the unit Newton per meter square, same as stress, as strain is unitless. Now let us consider a wire on which deforming force is applied in such a way that its length increases. Now generally if its length increases, its radius will decrease. Let us consider the increased length is dl and the decreased radius is dr. So whenever the deforming force is applied on a wire, its length increases and its radius decreases. So two types of strains are produced, longitudinal strain and lateral strain. And longitudinal strain is nothing but the ratio of change in length per original length, and lateral strain is nothing but the ratio of change in radius to original radius. So the ratio of these two strain is known as Poisson's ratio, which is unitless, which is dimensionless. So Poisson's ratio is the ratio of lateral strain to longitudinal strain. Lateral strain is delta R by R, longitudinal strain is delta L by L, or dr by R or dl by L respectively. And this negative sign in the expression you can see indicates the inverse relationship between change in length and change in radius. So this is Poisson's ratio.